Hello, my name is Eric Sanchez, and today I will present our work titled Mathematical Modeling for Mesoscopic Computational Analysis of Droplets using Morse and Coulombian Potentials, carried out in collaboration with Dr. Francisco Delgado at Tecnológico de Monterrey. The main idea of this research is to simulate the formation and interaction of droplets at the mesoscopic scale. That means we focus on systems that are larger than molecules but smaller than macroscopic fluids. Our aim is to reproduce the key physical behaviors of nanomotions without requiring millions of particles as in atomistic simulations. Nanomotions are dispersions of one liquid within another, stabilized by surfactants, where the droplet size is typically below 200 nanometers. They are classified into two main types: oil in water nanomotions, where the water corresponds to the continuous phase and the oil is the dispersed phase, and water in oil nanomotions, where oil is the continuous phase and water is the dispersed phase. Nano and micromotions have been widely applied in many industrial and scientific areas, for example, in pharmaceutical delivery systems, food formulations, cosmetic products, and also in polymers. The reason they are so relevant is because their small droplet size increases stability, solubility, and bioavailability of the dispersed phase. However, the behavior of these systems, their formation, stability, or interactions are extremely difficult to analyze experimentally. That's why we turn to simulations. They allow us to isolate key parameters such as interfacial tension or droplet coalescence and understand how they contribute to the global behavior of the nanomotion. Simulations are very useful to understand the behavior of the nanomotion's stability, formation, and also interactions. However, simulating them is very complex because of the huge number of interactions and particles present in the system. Each droplet may contain thousands or even millions of molecules, which can consume a lot of computational resources. In order to make the problem tractable, we work in a mesoscopic regime. That means we don't simulate every atom, but rather groups of atoms or entire droplets represented by effective potential. This reduces the computational resource consumption while keeping the average behavior of droplets considering physical phenomena such as attraction, repulsion, and compaction. Our main goal focuses on developing a simple but accurate ab initio simulation that reproduces formation and multiple phase interaction using potentials that model molecular forces. Our study combines two potentials, the Morse potential and the Coulombian potential. The Morse potential considers the attractive and repulsive forces between particles within a droplet. When particles are close, a strong repulsive force is applied. If they are far away, the particles present a mild attraction between them. On the other hand, the Coulomb potential introduces repulsion to particles that belong to a different phase, simulating what happens between oil and water droplets in an emulsion, helping to reproduce interfacial stability. Thermal motion also was represented considering damping and Brownian movement with dynamical equations using Langevin formalism. All simulations were executed in Z for numerical performance, while the resulting data was processed and visualized using Mathematica. The Morse potential considers how particles attract and repel depending on the distance between one another. When the distance Rij is smaller than the equilibrium position Z, the potential is repulsive, preventing the particles from overlapping. Otherwise, when Rij is bigger than the equilibrium position, the interaction becomes attractive, and particles start to get closer. The constants delta and B infinity control the strength and depth of the potential, while R0 represents the equilibrium distance where both attraction and repulsion balance. By simulating multiple particles, we can observe how the droplets form as they attract into a stable droplet as time goes on, reproducing the behavior of a dispersed system. The next equation includes damping and random forces, following the Langevin equation. The damping term, proportional to velocity, acts as a friction coefficient. Increasing lambda helps the system reach equilibrium faster by dissipating kinetic energy. The term eta simulates Brownian motion, which are the random collisions between particles caused by temperature. At long times, the effect of Brownian motion is negligible, and the systems arrive to the final equilibrium. By increasing the number of particles in the system, the compaction of particles becomes more pronounced. By adding gravity to the simulation, this allows the droplet to settle into a infinite potential surface. This enables us to measure the contact angle, which is a key quantity in wetting and hydrophobicity. By adjusting the values of V infinity and delta, the fluid can become more hydrophobic or hydrophilic. An example is shown below, where by applying a delta of minus 0.5, the droplet spreads more with a larger contact angle. The middle, with delta 0.5, compacts more, and at delta 3.5, with a higher V infinity, the droplet becomes almost spherical. Finally, we simulated a two-phase system, which represent the basic behavior of an emulsion. Here we have two types of particles, A and B, interacting via Morse potentials within each phase, but with an added Coulomb repulsion between one phase and the other. This represents the interfacial repulsion between immiscible fluids. The simulations were done with the same amount of particles of each type confined in a small cubic cell. We can see that depending on the repulsion generated by the Coulomb potential, the particles can stay together as miscible substances. They can partially mix, or they can also simulate immiscible phases, such as water and oil. This demonstrates that our simplified model successfully captures phase separation and interface formation, which are essential features of emulsions. To conclude, the Morse potential successfully reproduces droplet compaction at the mesoscopic level. Also, coupling with a Coulomb potential enables a stable two-phase interface formation. Additionally, increasing the quantity of particles enhances compaction and stabilizes the droplet's geometry, while the inclusion of gravity allows modeling realistic compact angles consistent with wetting phenomena. We plan to extend the model to include amphiphilic or surfactant-like particles to simulate nanoemulsion stabilization. Also, introduce density-dependent potentials or particle mass variations to study sedimentation and buoyancy. Finally, also, applying the model to specific systems for predictive industrial simulations. Thank you for your attention.